In order to better appreciate the importance of synchronization, we'll be looking at a very common synchronization problem in operating systems known as the producer-consumer problem. The idea here is that we have one or more processes or threads that are producing data and storing it in a buffer. Meanwhile, one or more consumer threads are consuming that data. We have to make sure that only one thread or process is accessing the buffer at a time, and that we don't produce more data than the buffer can hold, nor do we consume data from the buffer when it is empty. So the idea is that we have some fixed size buffer, which is simply an array of length n, and so there are n entries and we're using 0 indexing. So we have this buffer, and we are going to gradually add items to it. That's what the producers will do. And while the producers are adding more and more data to this, the consumers will extract data from the end. Now, eventually, the producers will reach the end of this array, and what we're going to do is wrap it around and treat this as a circular buffer or circular array. So if the producer has already placed an item in this last position and then wants to add a new item, it will be added at the front. Now, this can only be done if the item that was at the front earlier has been consumed by one of the consumer threads. So we have to make sure that the consumption stays ahead of production, but we also have to make sure that we don't start consuming things that haven't been produced yet. So overflow would be when we produce so much data that we overwrite some data that hasn't been consumed yet. Underflow would be if we consume something that hasn't been produced yet. We want to avoid both of these problems. Some of the hassle of managing this data structure can be abstracted away by simply treating it as a queue. However, in the low-level context where we often need to solve this problem, namely in operating systems, we generally don't want to have too much abstraction because we want to make sure everything functions as quickly and efficiently as possible. But even if we have that level of abstraction, we still need to provide synchronization. And so I'll be providing solutions to this problem using both semaphores and monitors with condition variables. This is a solution to the producer-consumer problem using semaphores. Now, the code is broken up into 3 sections, but that's only done to fit all the code on the screen. All of this code belongs in a single source file from top to bottom. This line followed by these lines followed by the main. Now, of course, this is pseudocode, so you'd have to change it to make it work anyway. The way it works is that we have a buffer size, which is some fixed size. That's the size of our circular buffer. And then we have 3 semaphores. Now, the semaphore S starts at 1, and all it really does is control access to the buffer. It's really only providing mutual exclusion. Now, the semaphores N and E are providing synchronization. They help the producer and consumer threads communicate with each other. N is going to prevent underflow because it indicates the number of items in the buffer that are available for consumption. And as it goes negative, that will indicate the number of threads that are waiting to consume things but are blocked. In contrast, this semaphore E is the amount of free space left in the buffer. So it will prevent overflow because as items are added to the buffer, this number will go down. Notice that it starts off at the buffer size. And when it goes below 0, that indicates the number of threads that would like to produce something and add it to the buffer but are blocked because it's already full. So here is our producer process or thread, and we have a while loop, and we're going to loop as long as we're able to produce. So this is some condition that will make sense in the context you're using it in. You could simply have while true here, but more generally, we're looping as long as there's something that can be produced. And so what we'll do is some command produce will produce and return a value and save it in a variable x. And then, because we want to add this to the buffer, we're going to wait on the semaphore e. Now, e starts off at the buffer size, and waiting decrements it, so as long as there is room left in the buffer, decrementing it won't cause any problems. It won't cause any blocks. We'll simply decrement that to indicate that we need to use up a slot, and we'll continue on. Then we do a wait on S. Now remember that S controls overall access to the buffer and provides mutual exclusion. In fact, these calls to the semaphore S, to both the wait and the signal here, could easily be replaced by a mutex lock. The wait is essentially a lock command, and the signal here is essentially an unlock. Because with a value of 1, waiting sets it to 0, meaning that if any other process tries to execute semWait on S, then that process will block. So we can view this here as being a very tightly associated critical section where we lock and then unlock access to the buffer. Now, after locking access to the buffer, we append that newly produced value x to the end of it. And so append is once again some command that is defined elsewhere that takes care of the nitty-gritty details of managing the buffer. Then, once we have appended a new value to the buffer and we've unlocked access to the buffer by signaling on S, we then do a sem signal on N. Now remember that N prevents underflow. N indicates how many items are available for consumption. So it starts off at 0 because the buffer is initially empty. But when we signal on N, we're indicating we're going to increment this variable, thus incrementing that something is now available to be consumed. So this signal command is a way of communicating to the consumer thread, which we'll discuss in a moment, that it can consume something. So going over to the consumer thread right now, we have a similar structure where we loop while there is still something that can be consumed. So this loop keeps going over and over and over again as long as there's something to consume. And the first thing it does is wait on the semaphore N. So you can imagine that if these threads are running at the same time, if the consumer reaches this command first before anything has been produced, then the consumer will block, because with an initial value of 0, this semWait command will decrement N to -1, and by the rules of semaphores, that causes the thread or process to block. So it's forced to wait until something is actually produced. Now, if this doesn't block, it means that something was previously produced, and we can continue. And so we first wait on the semaphore S, thus gaining mutually exclusive access to the buffer. So we have, once again, this sort of structure here where we're going to lock the buffer, and then this sem signal S will unlock it. And while this process or thread has mutually exclusive access to the buffer, it will take out the next value and store it in a variable x. So in terms of the data structure we're manipulating, this append is like an enqueue command on a queue, and the take is like a dequeue command on the queue. So we take out x, and then we unlock access to the buffer, and then by taking out x, we've created a new space in the buffer for something to be produced, something to be added. So we will then sem signal on E. So remember, E is tracking how much empty space there is, and so we've created a new empty space with this take command, and so we now signal that so that a producer can go forward and produce more items. In fact, if we had filled the buffer, let's say that the produce loop here ran as many times as the buffer size, then eventually it would get to a point where this semWait command would block, because we would consume, or rather we would decrement this variable enough times that it went to 0, then we would decrement it one more time, it would be negative, and the thing that would increment it and enable more items to be produced would be this semSignal command here. Now, after we've signaled that room has been made inside the buffer, we then consume the value x that we already produced, and consume depends on the specifics of your particular problem. So this semSignal command is meant to communicate to this semWait. So if a consumer had blocked because it was waiting at this point, this semSignal would tell that blocked process that it can continue from this point forward. Similarly, this signal goes back here, telling a process that became blocked when it tried to produce something that it can now continue producing things. So that is the back and forth communication of these synchronization operations. And then we have the main function here, and so we're doing a parallel launch of one producer and one consumer. That is the bare minimum for this code to work. However, you could have multiple producers and multiple consumers, and this exact same code would work fine regardless of how many producers and consumers you have, because they provide mutually exclusive access to the buffer via control with the semaphore S, and this semSignal could communicate with any of the semWait commands in any number of different consumer threads. Likewise, this semSignal in the consumer could communicate with any number of semWait E commands in any number of producer threads. Now there's one more important takeaway here, and that is that although we have this produce command and this consume command outside of the critical sections of the code, you could conceivably want to move this into the critical section. It essentially depends on exactly how you're producing things and how you're consuming things. But you'll get more efficiency if you're able to avoid keeping this in the critical section, similarly with the consume. So it depends on the particular problem and what you're producing, how you're producing it, and how you're consuming it. So this is a semaphore-based solution. Let's now look at a solution using monitors and condition variables. Now start by recalling that a monitor is a separate bit of code removed from the actual main body of the code. The monitor is an encapsulated structure in a programming language that has some functions or methods associated with it, to which access is mutually exclusive. So in this solution, we're actually going to define, at least in part, the append and take commands that were simply assumed to exist in the previous semaphore solution. So in this monitor class or entity, we have the buffer size defined, and we have two condition variables, one named not full and one named not empty. We're also going to maintain a count, which is the number of items inside the buffer. Now the append command that is similar to what was used in the semaphore solution but a bit more complicated, we're going to do some synchronization. Now keep in mind that simply by virtue of being inside of a monitor, access to this append command is already mutually exclusive. So simply by calling append, it's very similar in the previous solution to doing semWait on S and semSignal on S. So we enter append. We want to append a particular object X to the end of the queue, to the end of the circular buffer, And so what we do is we loop as long as the count, the number of objects in the buffer, is equal to the buffer size. In other words, if the buffer is full, then we need to loop, and what do we do in that loop? We wait. So we are waiting for the buffer to not be full. So not full is one of our condition variables, and so we're waiting until the buffer is not full. Now when this code starts, as you'll see in a second, the buffer will of course be empty, so this will be false. We'll skip right through it. I've left out details of the implementation, but some code would be here that adds an item to the end of the buffer. And after adding that item, we also need to increment our count because it's important for tracking the synchronization. And then we use cNotify on this not empty condition variable. So we are telling any other processes that need to know that because we have just added something to the buffer, it is not empty. Now, it may already have not been empty, but we're just indicating that it's definitely not empty now. So we either went from being empty to being not empty, or we went from being not empty to still being not empty. But we've sent this notification, which is something that could be listened to or waited for by this take command. So this take method is, once again, similar to what we had in the semaphore solution, but a bit more complicated because it's inside the monitor. And the take command starts off with a while loop. It says while the count is equal to 0. So in other words, as long as the buffer is empty, we're going to wait for it to not be empty. So this is our second condition variable. And as long as the buffer is empty, we are waiting. But once cNotify has been executed once, this will send a signal that can be caught here, at which point any blocked thread or process would become unblocked. And the reason for this while loop is that you may have multiple different producer and consumer threads that all want to grab access to the buffer as soon as it becomes available. And so even though you've just been told that the buffer is not empty and you can consume something, the while loop forces the thread or process to check one more time to make sure that the count is still not equal to 0 before moving forward. Because in the tiny interval when these different processes are released from their blocked queue, you don't know which one of those processes will swoop in and actually be able to execute. So they all need to do one last check to make sure they're allowed to continue. But one of them should be able to get through, and then we'll execute some code. I've left it out, but essentially we're going to take the next item from the buffer, we're going to store it in a variable called x. We're going to decrement the count because there is now one fewer item in the buffer, which means there's space to add more things. We will notify other threads of this fact, so we do cNotify on not full, which can be caught here. So if the buffer had reached a point where it was full, then this cNotify not full would allow any blocked threads here to go forward. And then we return x. Now this code is only for the monitor. We have to combine it with some actual main program code, but the main program code is fairly simple now because we have a monitor m, and then this is our producer thread, that's our consumer thread. We have our while loop that says as long as we can still produce, keep looping. And all we do is we produce a value x, and then we do m.append of x. So this calls this method here. And then in the consumer thread, we have a while loop, and we start off with a take command. And so m is our monitor, and so we take a value, and that is this code here. and then once we take the value, we consume it, and the loop continues. And then the main function is the same. We do a parallel launch of a producer and a consumer, but as I said before, there could be multiple producers and multiple consumers, and that wouldn't cause any problems. So although overall this code in combination is a bit longer, the actual main body code here is far simpler because of the abstraction of having a monitor. Now, of course, even if you don't have a monitor, you can simulate this by using mutexes, as we saw previously in a different video. But let me comment briefly on the similarities between this solution and the semaphore solution. So this C weight on the not full condition variable is very similar to the sem weight on the semaphore E in the semaphore solution. Similarly, the notification on the not empty condition variable is very much like the signal on the semaphore N in the semaphore solution. And in the consumer, we have a wait and a signal command as well, just like we have a wait and a notify in the take command of the monitor. So the not full condition variable is behaving like the semaphore E for the sake of synchronization. And the not empty condition variable is behaving like the semaphore N in this solution for synchronization. And as I mentioned briefly before, the reason that the monitor does not have any sort of construct or condition variable corresponding to this semaphore S is that all the semaphore S is doing is providing mutual exclusion. So that doesn't have to be explicitly represented in the monitor because it's simply a given that by virtue of being in a monitor, access to the append and take methods is mutually exclusive. This is, if this were Java code, this would be indicated by the presence of the synchronized keyword. So it's as if I said that this method and this method are both synchronized. And so this is not Java code, this is pseudocode, but if you want to think of it in those terms, because these methods are synchronized, there is an implicit locking and unlocking of some shared mutex simply by calling these methods. And so that is the nice thing about the monitor, is that it implicitly provides mutual exclusion, which allows this code here, the main code, to be very, very simple. If you didn't have that implicit locking, then you would need to have sort of a mutex lock here and a mutex unlock here, and then the same thing would have to happen at these 2 points with a mutex lock and a mutex unlock. So that is how you can solve the producer-consumer problem using either semaphores or a monitor with condition variables.